So hello everyone. Today I'm going to talk about cosmology, and in fact during those two lectures I'm going to give today and tomorrow, I'll try to cover more of a oversimplified maybe, simple version and a realistic version. Today is about simplicity. So I guess you kind of know that cosmology is a discipline that involves many fields of physics like relativity, quantum, particle physics. And I must say that cosmology became a real science only since the last 60, 70 years. And that was possible due to some really good observations and tests we did. And of course, that was possible due to the technological improvements. And the other thing I should specify is that the approval of the community in this model building of the standard model we use today was really important during this process of, doing the observations, tests, building the model. And sometimes it was even really, really important. And it would be nice to show you this historical improvement of how we understood the universe, what we know about the universe, and how some ideas, some very bad ideas were really, people really liked them and kept them for some time. And for other periods, really, really good ideas were not liked just because of some philosophical arguments. Maybe people didn't like them. So it'd be good to, tell you the history of the cosmology and how we reached to this point. But I think we don't have that much of time. That's why I'll just follow the linear route of the textbook to tell you about the story. So I'll divide the lectures into two, simple version, real version. So today, I'll start with giving you a brief review of general relativity. And then I'll show you some hacks to solve the Einstein field equations, which are applicable, which is the equation of general relativity. And how we apply those hacks to understand the universe. And that is basically applying some assumptions on the universe. And then I'll give you some brief summary of the standard cosmology we use today and the relevant observations to get the parameters of the standard cosmology we use. Tomorrow will be about the reality check. I'll talk about the problems of the standard model that we call lambda CDM. Lambda refers to the cosmological constant. CDM is the cold dark matter. And I'll talk about the alternatives to the standard model in terms of alternatives to the general relativity, maybe, or the standard cosmology we use today. And then I'll show you some pictures of the real cosmos rather than the simplified cosmos, and give you a brief summary of the inhomogeneous cosmologies, which I think is a good alternative to the standard model, and try to give you some summary of that. Okay, lecture one. It's a spherical cow. If we want to understand the standard model of cosmology we use today, we need to understand a bit of GR, and I'll try to give you the brief summary of the basic concepts, some basic mathematical constructions, and the physical concepts that you need to have an idea of, to grasp the idea. Okay, GR starts with space-time. It's a four-dimensional space-time with 3 dimensions of space and 1 dimension of time. And at every point of your space-time manifold, you can define local causality. That means you have a light cone that the information propagates, that the photons lives on. And the particles that moves slower than the photons lives on causal curves. You have cause and effect. And the regions that cannot be connected by causal curves, we'll call them spatial regions. And the other important concept in GR is the equivalence principle. That means locally, you can go to any frame, because in GR, all frames are equal, unlike the one in the Newtonian case. But you can always go to a frame where your geometry is flat. So imagine, by an analogy, imagine you're on the surface of a sphere. You can go to a tiny local region that you can assume it to be flat. And that is related to some physical concepts that you do your measurements on. For example, it is the local rest frame that is the rest frame with the Minkowski geometry where special relativity applies, is the place that you do your real measurements. And on those frames, you define your physical clocks. This is the concept of proper time. Rather than using any coordinate time, you use a proper physical clock in order to make your measurements. And the same thing applies for the proper length. It is the physical ruler you use to make your measurements in your local rest frame. The other important object is the geodesics. It's the generalization of the straightest line, shortest distance between 2 points. And these 2 points are space-time points. They are not spatial points. That means you need to be always thinking about four-dimensional curved geometry. And those curves, those geodesics can be space-like, time-like, or null, just like the geodesics that the photons propagate along. So they have different causal structure. The other important concept is geodesic deviation. So in general relativity, we don't have acceleration really, we have curvature instead. But when let's say there are a group of observers falling into a black hole, let's say, and if they want to measure the curvature of the space-time, what they need to measure is the deviation of the geodesics. Say you shoot two geodesics from the North Pole to the equator, and at each point you can measure this deviation of the geodesics, and that's how you get the idea about the curvature actually. Okay, let's switch to mathematical objects, important mathematical objects for GR. The first one is the metric field. In general relativity, metric field is the gravitational field. There's no background, no nothing. It is the geometry that specifies what the actual gravitation of your system. And it has 3 dimensions. You can pick the notation however you wish, either minus referring to the time-like direction, and then you have plus, 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 or you can switch the signature. For example, this is a metric of a static black hole, a Schwarzschild black hole with a coordinate singularity. And if you want to find the magnitude or inner product of vectors, you use the metric tensor in order to find it. And again, those vectors have different causal structures. They can be time-like, space-like, or null. The next important object is the connection. So if you remember from the high school physics, the vector analysis, if you want to add 2 vectors, you can easily take one vector and then carry the other vector to another point to have an addition, right? So this is only possible, this carrying of the vectors to another point is possible because in Euclidean geometry, the basis vectors do not change. You go to another point, you can use the same basis vectors. But if you have a curved geometry, the basis vectors changes when you move your vectors from one point to another. So you need to define an object, which we call the connection, or Christoffel symbols if you have the symmetry, of how your basis vector change when you move it from one point to another. So this is a very important object. For example, okay, this is not good quality. If you want to find the change in your basis vector in the radial direction, you have these Christoffel symbols that you need to use in order to find out how your basis vector in the r direction changes with respect to the change in the theta direction, and you get the components of each bit. So this is important to define a covariant derivative. So we're after derivatives, but it should be defined covariantly. It should be defined in a manner that it's not depending on any coordinate system, any frame whatsoever. So, and I already told you that the basis vectors change once you move things, like when you take the derivative. So if you want to define a derivative, you first take the portion with the partial derivative of your vector itself, defined at that point. And then there's this portion that is due to the change of your basis vectors. This is how you define a derivative operator in a covariant manner. Now that is important. Covariant derivative operator is important to define Riemann and Ricci curvature tensors. In a Kurt's geometry, let's say you want to move a vector from one point to another. When you transport your vector through one path, and then you want to reach to the same point through another path, you end up with different vectors. That's the whole idea of curvature, actually. So that's why the commutator of these covariant derivatives gives you the idea of the Riemann tensor here. Well, what you do is you transport your vector in one direction and then the other, and then you switch. You take the commutator, and that gives you idea about how your space-time is curved. So this is a 4-rank tensor, and it is a function of this connection that I mentioned before, partial derivative of the connection and its multiplication, second-order connection, let's say. The connection itself is a function of the partial derivatives of the metric. So where I'm reaching is this Riemann tensor, Riemann curvature tensor, is a function of up to second-order derivatives of the metric. That is important. And then you define a Ricci tensor by contracting the first and third indices, and a Ricci scalar by further contracting the indices. And those will be the important objects to define the Einstein field equations. So GR means basically Einstein field equations. That means we have the geometry on the left-hand side with the curvature terms that I already mentioned. And on the right-hand side, you have the source fields. It can be matter. It can be electromagnetic radiation. So the source field is given by a 4x4 stress energy tensor. So the time-time component gives you the energy density. The time-space components gives you the energy fluxes. The space-time components gives you momentum density. And then you have, in the spatial components, you have the shear stresses, momentum fluxes, and the diagonal gives you the pressure terms. For example, the simplest you can get is the stress energy tensor of a perfect fluid. You have just the diagonal terms with the energy density and the pressure terms. Or let's say the electromagnetic field, as you see, the time-time component gives you the energy density. And so S is the Poynting vector. Here you have the Poynting vector components. And in the special part, you have the Maxwell stress energy tensor. So in order to have a grasp of what these Einstein equations are, I'll use an analogy with the Newtonian case, which we all know. So in Newton, let's say you have a ball of particles, you know the total mass, you know the volume, you define the energy density. And given that energy density, you put it in your Poisson's equation and solve for the gravitational field. Gravitational potential, sorry. And the divergence of the gravitational potential gives you the forces. And through the Newton's equation, m times acceleration is equal to force. You can get the dynamics of your system. You can find the positions of the particles. Now in GR, you have the stress energy tensor that I mentioned. You know the energy densities and the pressures, let's say, for a perfect fluid. And you plug it into the right-hand side, solve for this partial differential equation, and you solve for the metric. That's how you find out about the metric field, which is basically your gravitational field. And in order to find how particles move, you put it in your geodesics equation. If it's equal to 0, it gives you the geodesics, like free falling particles, let's say, for the time-like case. And if this equation is not equal to 0, then you get force-like terms. And that's how you get the dynamics of the particles in general relativity. Now, as I said, Einstein field equations gives you the relation between geometry and the source field. So plainly, we say that matter tells geometry how to curve, and geometry tells matter particles how to move. It's a coupled equation. So this coupled nonlinear equation is hyperbolic elliptic, and geometry and matter fields are dynamical. That means exact solutions are often a challenge. I mean, for realistic situations, you cannot really find exact solutions to this equation. It's really hard. But there are some hacks to solve Einstein field equations. And the first one would be, no surprise, linearization. You go to a weak field limit. Let's say you have a metric, a generic metric, in the weak field limit. You can write it as a Minkowski metric plus a very small perturbation around it. And let's say you have a harmonic gauge. Then this Einstein field equation becomes a linear wave equation, which you can solve easily. Then you have the gravitational waves. And the other way to solve Einstein equations is to give the system some symmetries. You introduce symmetries. For example, for a static, spherically symmetric system, you can find the solution for a static black hole. And it was easy. Just a year after Einstein found the general relativity, Schwarzschild could come up with such a solution. But if you lose just one symmetry of the system, that means if you let your black hole to rotate this time, your system becomes stationary. And it took us to find the solution nearly 50 years when you lose just one symmetry. And it was a big thing when Roy Kerr came up with the rotating black hole solution. Now, so we kind of know the hacks to solve the Einstein equations. We'll apply this to cosmology. And that will be by introducing symmetries. This will give you, I mean, you'll end up with physical assumptions corresponding to the symmetries, of course. And that is, universe is homogeneous and isotropic. This is the cosmological principle. It says that we are at just an ordinary position in the universe, right? If it's purely homogeneous and isotropic. And then you assume that your galaxies in the universe, or for now, let's say, are particles, just dust particles. You assume that you can define a perfect fluid corresponding to this system with a very easy stress energy tensor. And you further assume that the universe is expanding adiabatically, so that you can apply very simple thermodynamic relations. So, as I said, once you plug in your stress energy tensor on the right-hand side and solve for this system with high symmetries, homogeneous and isotropic, you end up with a very simple solution, which is found by Friedman, Lemaitre, Robertson, Walker. And here's your metric. You have Euclidean metric, which expands with some scale factor. And that is the basic gravitational field that we use in cosmology. Now I'll try to just quickly show you why I call it so simple. So in general, this gravitational field, your metric tensor, is a 4x4 matrix. And since it's symmetric, it's governed by 10 functions. And in order to find the Einstein equations, you compute your curvature tensor. So it's a 4-rank tensor in 4-dimensional space-times. That means it has 4 to the 4 components, 256 components. And then once you contract this Riemann tensor to get the Ricci, you get huge terms in general. Then you need to solve this highly coupled equation, 10 equations for 10 unknowns, which, as I said, really hard. So in cosmology, this metric you have is governed by just one function, which is a function of time only. And the curvature terms, the Ricci tensor terms, are just a few, and they're really simple functions. So you end up with those two equations corresponding to Einstein's field equations, which are ordinary equations with really small terms. That is this simple that you can get. Now, if you want to find out about the evolution of the scale factor, how the universe evolves, you can just consider your energy density as the energy divided by your volume. And volume is, of course, proportional to 1 over a cubed. Because remember, it was the scale factor giving you how much the universe, this Euclidean geometry expands. And for generic equation of state that relates pressure to the energy density, you have a constant omega factor, which you can find out the solution of this A, just solve this equation and the previous one that I showed, and you get a polynomial function for the expansion of the scale factor depending on the equation of state. That means for different kinds of fluids, you get different solutions. And in fact, in different cosmological eras of the universe, different types of fluids dominate. For example, in the early universe, the radiation dominates, and the equation of state, omega is 1 over 3, and once you plug it, you see that the scale factor goes with t to the 1 over 2. And later, the dust matter dominates, and it's pressureless. Then you get your scale factor going t to 2 over 3. And at the later times, the dark energy term dominates, which means you have vacuum-like energy, and the scale factors goes as an exponential function. Now, just by this simple analysis, you can get the idea that the universe is dynamic, those two properties. And the second one is when you go to the time is equal to 0, you hit a singularity, which is Big Bang. Now, so in this simple model, we usually tend to use a grid that expands with the galaxies itself. So imagine you have like a homogeneous and isotropic distribution of galaxies. You put a grid that expands together with these galaxies that we say it's a co-moving frame. And the physical distances between them would be just the multiplication of the scale factor and this constant grid distance, right? Because if galaxies are always staying at these grid points, they will have fixed location. And to find the rate of this distance, which astronomers usually refer as velocities, but in fact they're not velocities, it's the space that expands. It's not like the galaxies are running away, it's the expansion of the space. Then you can find a relation between the velocities and the distances, and the parameter that relates them is called Hubble's parameter, because it was Hubble who crudely tried to find out the relation between this. He observed the nebulas. He plainly just plotted distances between nebulas and the distance to the nebulas and their velocities, and he get a linear relation in order to find it, and that's why we call it the Hubble's parameter. And since I mentioned, okay, I should tell you this. So he found that the magnitude of the Hubble's parameter to be 550 kilometers per second per megaparsecs, and it's off by nearly an order. Nowadays, it's nearly this parameter is nearly 70, and the reason that I'm saying nearly 70 will be obvious more tomorrow, because there are some discrepancies. You cannot just say that this is the Hubble parameter when you look at this direction. So all I can say is it's off by an order. And since I give you some units, maybe I should give you some scales as well. Okay, the distance between the Sun and the Earth is called 1 astronomical unit, and it's 4.85 times 10 to the minus 9 kiloparsecs. The size of our Milky Way, our galaxy, is around 30 kiloparsecs, and our location from the center is 8 kiloparsecs. A typical size of a galaxy cluster is around 2 to the 10 megaparsec, and the size of the observable universe is 28.5 gigaparsecs. I mean, just to give you a crude idea about those scales. Okay. So now I'll talk about the redshift, luminosity distance, and the acceleration of the universe. So since galaxies, the universe is expanding, and the galaxies are expanding with this grid that I mentioned, when they send signals to each other, the wavelength of the signals gets expanded as well. That means the signals are redshifted. We call it the cosmological redshift. And redshift, you find out the redshift by comparing the emitted redshifts to the observed ones. And once you plug it into the relation that I mentioned before, you see that this redshift is proportional to the scale factor. As the universe expands, your wavelengths increases, basically. And 1 over redshift, which is the ratio of the observed wavelength to the emitted one, is the A0, a scale factor that we measured today, to the A that's when it was emitted, basically. And the luminosity is the, let's say, flux is the luminosity per area, right? Observed area. And you can get an idea about this luminosity distance, which is relevant for your observations itself, the physical thing that you see with your telescope, by this L, the physical distance I mentioned before, corrected by this redshift factor. Now, this is important to understand the acceleration of the universe, and let me just walk you through how it's related. Let's start with expanding our scale factor near the point that we measured today. And let's go up to the second order. Now, if you substitute this expanded scale factor into the redshift relation that we derived, you get an equation for the redshift in terms of the Hubble's parameter, which is A dot divided by A, remember, the luminosity distances, and you have the quadratic order terms, and you have this Q term, which is the deceleration parameter. So if your deceleration parameter is negative, that means universe is accelerating. Now, you solve this equation for the luminosity distance, and you get such a relation. I just kept it up to second order with respect to the Hubble's parameter, the redshift, and the deceleration parameter. And if you look carefully, this is just the portion that Hubble was considering, just the linear portion. So that's what people in the supernova experiment use, basically. Because supernova 1A is a really good standard candle. They have the same peak brightness. That means you know the absolute magnitudes, and if you can measure the apparent magnitudes, there's an empirical relation that gives you directly the luminosity distance without assuming any model. So that's why supernova experiments are really important in cosmology. And through the shifts of their spectra, you can find out the redshifts. And you can plot the observed, the luminosity distance redshift relation. And when you compare it to the equation that I write here, when you compare those two plots, you can see that the deceleration parameter is negative. That means universe is accelerating. And that was done by two groups, one from Australia, the other from US in 1998. And they got the Nobel Prize 13 years later with this discovery. Now, and then you go and ask, what changes the behavior of the scale factor in general in your model? And how should we modify the model so that we have this accelerated expansion in our standard model, let's say, cosmological model. But let me just first talk about the spatial curvature, because it's one of the reasons to change the behavior of the scale factor. Previously, I said that the simplest solution that we have is this FLRW geometry with Euclidean spatial slices. But in fact, for a generic solution, you can get 3 different kinds of curvature that you modify your metric with this k term, little k, so that your spatial slices can be positively curved, negatively curved, or they can be flat, as I mentioned. And that depends on how much amount of matter or energy density you have in your domain. So if your energy density is close to some critical value, you have the flat geometry for your spatial slices. If you have more matter in the universe tends to collapse into itself. You have positive curvature. And then if you have less matter than the critical one, you have negative curvature. So how does this affect the evolution of the scale factor? So remember, this is the Einstein equation when you have no curvature, when you have flat slices. And when you look at the mean distance between galaxies to the time, you see the evolution of this scale factor in general. When you include curvature terms, those 3 options in your model, you see other behavior in the mean distances between galaxies. So if you have more matter than the critical one, at one point universe collapses on itself. If you have less matter, you have a more slightly different distribution. But still, you cannot model acceleration by imposing just curvature into the system. For that, you need to add an additional term that we call the cosmological constant. It's a fixed constant that you put, and that gives you the acceleration term in your model. That is also called dark energy, and no one knows what causes this, what's the physical, real physical mechanism behind it. But the standard cosmology just assumes it to be some scalar field that is plugged to the Einstein equation by hand. So, that is the governing equation of cosmology, as I said, and those are the basic ingredients. So, rho b is the energy density that is corresponding to baryons. Then you can add some cold dark matter particles to your system and radiation. And then you have terms including the curvature of the spatial slices and the dark energy term. And for each of them, you can define dimensionless parameters. Those will be the parameters of our current cosmological model. So we're after the Hubble's parameter that we measured today. The index 0 refers to today, which is A dot divided by A. And then you have the dimensionless parameters for the baryonic, cold dark matter content, radiation, curvature, and dark energy. If you can fit them to your observations correctly, you have a well-working model. So how to best obtain this data set of your cosmological model? The answer relies on the early universe. And in order to explain that, I'll give you a brief summary of the hot Big Bang, which includes, again, simple thermodynamics. So we assume perfect gas and perfect gas equation. And we know that we keep in mind that the volume goes with cubic order of the scale factor. Then we also assume adiabatic expansion, which means this relation holds, with gamma being 4 divided by 3, because early universe is dominated by photons. It's the photon pressure. And when you write the equation for pressure in terms of volume, plug it into the equation on the upper line, and keeping in mind that the volume goes with the order of 3 for the scale factor, you solve for temperature. And you see that temperature is inversely proportional with the scale factor. That means as the universe expands, the universe cools down. So initially we had this photon baryon plasma at the early universe. And in that, protons couldn't couple to electrons because of Thomson scattering, basically. They were too energetic. But as the universe expanded a bit and it cooled down, protons could combine to the electrons. And in the meantime, photons were able to free stream from this plasma. They could just escape, something like that. So we call this period the period of decoupling or recombination. And we can see this relic radiation on the sky as the cosmic microwave background radiation. You can turn your antenna in any direction on the sky and you will see this background radiation in the universe. It's almost isotropic anywhere you look. And that happened when the universe was at the age of 380 years nearly. So this microwave background radiation is a Swiss knife for cosmology. You can get a lot of information, and many people are working on this field. When you ask them if you're a cosmologist, they do know about how this cosmic microwave background is relevant for cosmology. It's really important. So this is a blackbody spectrum with the average temperature of 2.7 to 2 kelvins. It's really cold. And it was discovered in 1965 by two scientists. They were working in the Bell Laboratory, actually. And they were trying to find some optimization of satellite data. And they had this noise in their data, you know, and they were trying to get rid of this data. And in time, they were really persistent to figure out what this noise is. And as time goes by, they found out that it's actually radiation coming from the early, coming from the universe itself, not a mistake or the antenna noise or anything. So this is the Kobe satellite data. It has a perfect blackbody spectrum. And now we just don't have the temperature data for the CMB. We have the polarization and lensing data. And by these data, you get the geometry, contents, and the initial conditions of the universe. And you can idea about what happened at the start of the expansion and the properties of the dark sector. That is, you get an idea about how much dark matter we have, what's the energy density of the dark energy, even some information about neutrinos. So, I said that this observation is done in every direction in the sky, but there are some anisotropies. It's not perfectly isotropic. And here is the sky map given by the Planck team, which is the famous team in cosmology. And you can see the anisotropies in the temperature. Now, causes of this anisotropy is the primordial quantum fluctuations. In the very early universe, after the Big Bang, there was this fluctuations in the gravitational field, and after this decoupling of photons, the photons carried this information in the fluctuations of the gravitational field, and that's why you have this temperature anisotropies. They're Gaussian, random anisotropies. Those are the primary effects. And then you have the secondary effects that affect the photon path, like reionization, the hot gas clusters, evolving potential wells, or the gravitational lensing that affects those anisotropies in the photon path. Okay, in order to map this, what you do is, N is the line of sight. In every line of sight, you measure your temperature, and then you take the sky average of the temperature. Then you define this difference, anisotropy, for each direction. And you can expand this as spherical harmonics in order to get the map of the whole CMB sky. And then you get the power spectrum through the magnitudes of the coefficients, the squares of the magnitudes of the coefficients. And you end up with such a spectrum. So Vertical is the power, basically CL times 12 plus 1, versus the multiple moments. Okay, the multiple moment is inversely proportional to the scale you look on the sky. So the further you get, the bigger scale you have the sky, you go to the lower multiples actually. So it's like you can think of the angular scales getting bigger should be multiple moments getting smaller, inversely proportional. So this kind of anisotropy was actually guessed. There was a theoretical prediction just 2 years after the discovery of the CMB. And in order to have such a theoretical prediction, what people use a simple linear perturbation theory. So you solve the perturbed Einstein equations with perturbed sources, perturbed density field, perturbed velocity field. And you solve for a perturbed geometry. So those are the perturbations in the gravitational field. If you set them to 0, you end up with this generic homogeneous and isotropic solution. So what you do is give perturbed sources on the right-hand side, solve for the perturbed Einstein equation, and solve for the gravitational perturbations in order to find out about your actual gravitational field. Then what you do is you define a perturbed phase-based distribution function and perturbed Boltzmann equation. So C here is the collision factor. Since you solve for the perturbations in the gravitational field by Einstein equations, you can solve for those temperature anisotropies. So that was the theoretical prediction, just by a simple linear perturbation theory. And you can further expand this perturbations in the temperature into spherical harmonics, just like you would do with the data. And you get a theoretical power spectrum. Now what you do is just compare those predicted power spectrum to the observed power spectrum, and that's how you get the cosmological parameters. You have a theoretical prediction with some cosmological parameters, you have the observed power spectrum, and by trying to match them together, you play with your parameters, tune your parameters to the observation, and that's how you get the parameters of your cosmological model. So, for example, by fitting the first peak in this acoustic oscillations, they found out that the universe, the spatial sections of the universe is actually flat, so K is 0. And the relative heights of the second and the third peaks gives you idea about the missing non-baryonic mass. We assume it to be in the form of cold dark matter. For example, this is just a simulation from WHO. Just by playing with the baryonic parameter, remember this was the dimensionless parameter of the energy density. Just by tuning it, the baryonic content or the overall metric content, you can fit your model, just play with the relative heights of these peaks and get the idea about the parameters of your model. So that's what they did. For example, here the Hubble's parameter is shown as 16.88 kilometers per second per megaparsecs. For dark energy parameter, you see that it's 0.679, which means 67.9% of the energy budget of the universe is in the form of dark energy. Or the total matter is 32%. The age of the universe is around 13.8 billion. So CMB is, as I said, is a Swiss knife to understand the contents of the universe. It's really, really important. Okay, you can go and say, okay, I have an idea about the total matter of the universe, let's say. But how do I know that some portion is baryonic and some portion is non-baryonic? How do I know this difference? What tells me this? And that resides in, again, the early universe, the Big Bang nucleosynthesis, and the abundances of the light elements. So that happened during the era when the age of the universe was just 1 second, and the temperature was around 1 megaelectron volts. So at these high temperatures, there is thermal equilibrium, or you can assume thermal equilibrium. And that fixes the ratio of the energy number density of the neutrons to protons. Here, Q is the difference between the proton mass and neutron mass. So as the universe expands and the temperature drops down, this gamma factor, which is the interconversion rate per nucleon of the neutrons to protons, drops faster than the Hubble's parameter. So it goes with T to the 5. Here GF is the Fermi constant, and the Hubble's parameter goes with T to the 2, and Gn is the Newton's constant, gravitational constant. G star is the number of species you have that contributes to the Hubble's parameter. So since this interconversion rate drops faster, you have a departure from the chemical equilibrium, and there's a freeze-out temperature when this happens. And that fixes the ratio of the number density of the neutrons to protons. And by the time that happened, it was 1/6. And after the freeze-out, neutrons are free to beta decay, and then you have a further drop to 1/7. Then after this point, nuclear reactions begin. And the rate of these nuclear reactions depend on the ratio of the baryons to photons. And you can predict this with theoretical predictions, actually. So it's the light elements that are created in the universe. Like you have hydrogen, deuterium, helium-3, helium-4. You go up to lithium. Beryllium is really, really trace beryllium because it's not stable during those times. And okay, this ratio between the baryons to photons can be predicted by the abundances of the light elements. It's between 5.8 to 6.6 times 10 to the minus 10, and this is in the 95 confidence level. So with this, we know the mass abundances of the light elements. Like hydrogen is 75%, helium is around 25, and then you have 0.01, around 0.01 of deuterium and helium-3, and 10 to the minus 10 of lithium in the early universe. And now, the number density of photons is fixed by the CMB temperature. We know it, we measure it really well, and I already told you that it's a black body spectrum, so you can guess the number density of the photons. That means there's an allowed range for the number density or the energy density of baryons. We know it. We know it by the light abundances of the light elements, as I said. So it should be somewhere between 8.9 to 4.6 times 10 to the minus 31 grams per centimeter cube. So by the data of the CMB and the nuclear synthesis, you can get the idea of the total matter and the allowed range of the baryonic matter. That gives you idea about how much additional matter that is in non-baryonic form that you need in order to have that much of light elements in the universe we have today. So, for example, this is a plot from Sakar. In the vertical axis, you have the abundances of light elements per hydrogen, and the horizontal line gives you the baryon to photon ratio, and those curves gives you the abundances of the light elements for each ratio of the baryon to photon. And this is the narrow range set by the CMB. So just by using the early time nuclear synthesis and the Big Bang and the CMB data, you get the parameter that you need for the baryonic matter and cold dark matter. So I'll sum up. I think I'm too fast, but tomorrow will be different because we have a lot of things to discuss. So, this is the summary that I can give you. The universe started with a bang, Big Bang, and then you had some quantum fluctuations. Then there's this inflation period which took very tiny fraction of time, and it expanded the universe in a great amount. This is also a theory, and I'll talk about it tomorrow. And then comes the decoupling that I mentioned. Initially there was this photon baryon plasma in which protons and electrons couldn't combine because it was so energetic. But after some time, universe expanded a bit, it cooled down, and protons and electrons could couple. And in the meantime, photons were able to free stream. And this is the radiation that we observe today as the CMB, cosmic microwave background. It's all over the sky. And the anisotropies in that we map as the spherical harmonics gives us idea about the initial quantum fluctuations. It's, and whether we have it or not, what kind of, whether they're Gaussian or not, for example. And then there are dark ages, and the first stars starts to form. So the structure formation in the universe is bottom-up rather than top-bottom. So we now know that it was first stars that form, and then galaxies, and then galaxy clusters. And nowadays it's the dark energy, which is around 70% of the energy budget of the universe, which dominates the universe. It gives this accelerated expansion phenomena in the universe. That's what we call it. We do not know what it is. We do not know the physical mechanism behind it. But I'll talk about that tomorrow. What can be the alternatives? What can be the physical mechanisms behind it? Yeah, I think that's it for today. Thanks for listening.